It's a Spotify podcast.
You pushed me down, thought I'd stay on the ground, counting me.
One. Hey everyone, welcome to another episode of Rabbit Holes Deep Dive Issue. Tonight we're talking about fusion's moment of truth. Imagine a machine the size of a building. Inside it, matter is heated until atoms can no longer hold onto their electrons. The gas becomes plasma. Temperatures climb beyond anything naturally found on Earth. Hydrogen nuclei collide. They fuse. Energy is released. Then the announcement comes. Breakthrough. Fusion milestone. For the first time, or the longest time, or the greatest energy, or the highest gain, another barrier has fallen. And every few years, the world asks the same question. Is that it? Did fusion finally arrive? There's only one problem. Your house isn't connected to it. Neither is mine. No commercial fusion power station is quietly selling electricity down the street. And that creates one of the strangest stories in modern science. Humanity has spent roughly 7 decades learning how to make fusion happen. But making fusion happen and making fusion electricity are not the same problem. In fact, the closer we get to solving the first problem, the more obvious the second one becomes. Can the machine survive? Can we get the heat out? Can we manufacture fuel? Can we repair the reactor? Can we turn the energy into electricity efficiently? Can it run off enough to matter? And finally, can anyone afford the power? Those questions used to feel distant. But in June of 2026, the United States Department of Energy released a finalized fusion science and technology roadmap explicitly aiming at supporting pilot plants and commercial fusion power in the mid-2030s. Private money is flowing. National programs are reorganizing. Supply chains are being discussed. Materials programs are expanding. Pilot plants are no longer theoretical vocabulary. That does not mean commercial fusion arrives in 2035. It means the excuses are changing. For decades, fusion could survive a scientific promise. Now, increasingly, it has become an engineering product. And engineering is much less forgiving than hope. So tonight, we're not asking whether fusion is real, because it is. We're asking something harder. What could humanity actually have to accomplish before we could truthfully say commercial fusion power has arrived? Welcome to Rabbit Holes Deep Dives. This is where we read the research, follow the engineering, compare the promises with the evidence, and try not to confuse progress with completion. Because fusion may be approaching its most important test, not whether we can create the reaction, whether we can build a machine around it. The machine that works, but doesn't power your house. Let's start with the most important distinction in the entire episode. Fusion energy, fusion gain, and fusion electricity are not automatically the same thing. If you miss the distinction, almost every fusion headline becomes confusing. Fusion itself is straightforward in concept. Take light atomic nuclei. Force them close enough together, they combine. A tiny difference in mass appears as energy. The sun does this consistently. But stars have something fusion engineers don't: gravity. An enormous star crushes plasma inward with its own mass. We don't have that luxury. So human beings invented different ways to combine fusion fuel: magnetic fields, tokamaks, accelerators. So human beings invented different ways to combine fusion fuel: magnetic fields, tokamaks, stellarators, lasers, other experimental approaches. And over the decades, we've gotten increasingly good at creating fusion conditions. But imagine you're designing a car. One day you build the world's greatest engine. It produces extraordinary power. Everyone celebrates. Then someone asks, where are the wheels? Where's the transmission? Where's the cooling system? Where's the fuel tank? Can it run for more than 20 seconds? Can a mechanic repair it? What's the mileage? What's the price? You didn't fail. The engine breakthrough may be extraordinary, but an engine isn't a transportation system. Fusion plasma is similar. Plasma can achieve an incredible scientific milestone without the total facility becoming a practical electrical power station. And that's the gap in fusion industry now has to cross. One of the reasons this gets confusing is a letter: Q. Fusion researchers use different forms of Q to describe energy gain. In the simplest public version, energy out divided by energy in. But where exactly do you draw the box? Around the fusion target? Around the plasma? Around the heating system? Around the reactor? Around the entire power station? Those boundaries matter. Imagine a facility uses enormous amounts of electricity to run magnets, lasers, cryogenics, pumps, heating systems, computers, cooling, fuel processing, and everything else. The plasma might produce a spectacular fusion gain, while the overall plant still consumes more electricity than it sends to the grid. That doesn't make a scientific result fake. It means it answered a different question. And this is why the phrase net energy needs context every single time you hear it. Net where? At the plasma? At the target? At the wall plug? At the generator? At the electrical grid? The public tends to imagine one finish line. Fusion has several. Scientists have spent decades pushing through the physics finish lines. Now the industry is staring at the engineering ones. And that's where things get uncomfortable. Because once fusion actually works, the machine starts attacking itself. 70 years of getting closer. Fusion's reputation is unusual. Few technologies have ever been simultaneously taken so seriously and mocked so relentlessly. You've probably heard the joke: fusion is 30 years away and always will be. The joke survives because fusion programs have made optimistic predictions for decades. But the joke can also hide inside real progress. Early researchers had to learn basic plasma confinement, then stability, then heating, then magnet field control, then turbulence, then impurities, then plasma shape, then materials, then semiconducting magnets, then diagnostics, then computation. Every generation inherited a machine more sophisticated than the one before it. Tokamaks became larger. Stellarators became more precisely engineered. Lasers became more powerful. Superconducting magnets improved. Computer modeling improved. Manufacturing improved. And slowly, the question changed. Not, can fusion happen? But, can fusion happen under conditions useful enough for energy production? ITER, represents one of the largest attempts to answer part of that question. It is an enormous international tokamak under construction in France. But here's an important thing many people misunderstand. ITER is not designed to become commercial power stations supplying electricity to the grid. Its purpose is research. It is intended to study burning plasma, integrated fusion technology, materials, tritium breeding concepts, heating handling, and other reactor scale problems. Even if ITER's own public explanation says sustained fusion reactions are only one piece of the puzzle, I want you to think about that phrase. Only one piece. Because this is coming from people building one of the largest fusion experiments ever attempted. Their engineering list includes materials, heat exhaust, remote maintenance, tritium, electricity generation. Those aren't footnotes. That's the power plant. And ITER itself demonstrates another uncomfortable fact. First-of-a-kind machines are hard. The revised baseline presented in 2024 pushed major deuterium operations towards 2035. Now, critics look at that and say, see, fusion is always delayed. Supporters say, of course it's delayed. Nobody has built this exact machine before. Both observations contain truth. Complex engineering projects expose problems predictions didn't fully anticipate. That's not unique to fusion. Airplanes did it. Nuclear reactors did it. Space programs have done it. Semiconductor factories do it. The relevant question isn't whether delays happen. It's whether each delay teaches you how to build the next machine better, or whether the fundamental complexity keeps defeating commercial economics. And that's where fusion is approaching a new phase. Because private companies don't have the same luxury as science projects, eventually investors ask, when do we sell power? Governments ask, when does this strengthen the grid? Utilities ask, how reliable is it? Regulators ask, how do we license it? Customers ask, how much does electricity cost? That's why the 2026 DOE roadmap matters. It doesn't prove fusion is ready. It proves the institutional objective has changed. The roadmap talks about pilot plants, commercialization, infrastructure, supply chains, workforce, industry, not merely plasma science. The fusion story is being forced out of laboratory vocabulary and into industrial vocabulary. But industrial vocabulary has consequences. A fusion company can no longer point only at a beautiful plasma. It has to answer what happens to the wall around it. The problems after fusion. Here's the paradox. The fusion reaction everybody wants creates some of the engineering problems everybody has to solve. Consider deuterium tritium fusion. Two hydrogen isotopes combine. The reaction produces helium and a very energetic neutron. The helium helps heat the plasma. That's useful. The neutron escapes the magnetic confinement. Also useful. because that neutron carries energy outward where the reactor can potentially capture it as heat. But now that high energy neutron slams into materials over and over and over. Suddenly, the inner structure of the machine lives in a radiation environment almost nothing else experiences. Atoms get displaced, materials swell, properties change, components become activated. Structural integrity matters, cooling matters, lifetime matters. Now imagine building a power station that depends on those components for continuous operation. A laboratory can replace a part. A commercial utility wants a predictable maintenance interval. There is a huge difference. Then comes the heat. Fusion plasmas are incredibly hot, but temperature isn't the only problem. Power density matters. Where energy and particles strike surfaces, especially around components such as the diverter, the engineering challenges become brutal. The diverter is essentially part of the exhaust system. It has to remove impurities, handle particles, manage heat, and protect the rest of the machine. ITER says that these conditions are pushing present technological limits. That means commercial plants need materials and designs capable not merely of surviving one impressive experiment, but surviving repeated operations. Then there is maintenance. Inside a fusion reactor, you cannot simply send a mechanic in with a wrench. Radiation, vacuum, activation, complex geometry, heavy components. Maintenance increasingly becomes a robotics problem. Remote manipulation, remote inspection, remote replacement, remote recovery when something goes wrong. Think about the economics. If an internal component fails, how quickly can you replace it? Hours? Days? Weeks? Months? Because a power plant that is offline isn't generating revenue. Now, we arrive at one of my favorite hidden fusion problems. Fuel. The phrase fusion fuel often produces this romantic image. We have enough fuel in the seawater to power civilization forever. There's truth in hiding inside that statement. Deuterium is abundant, but most near-term fusion reactor concepts rely heavily on tritium too. Tritium is very different. It is radioactive. It decays. It isn't naturally abundant in the quantities a global fusion industry would need. So a future DT fusion plant may have to manufacture its own fuel inside the reactor. Here's how. Fusion releases neutrons. Those neutrons enter a blanket surrounding the plasma. If the blanket contains lithium, neutron interactions can create tritium. That tritium is extracted, processed, and fed back into the reactor. Elegant, right? At least on paper. But now imagine the practical requirement. The plant must breed enough tritium to replace what it burns, plus account for processing losses, plus maintain inventories, plus start future reactors. And the entire system has to work at industrial scale. ITER will test breeding blanket concepts, but ITER itself says that large-scale tritium production and recycling still requires further research. This is one of those sentences that completely changes the story, because fusion doesn't need a reactor. It needs a fuel economy. Then comes electricity. The neutron depends energy surrounding structures. That energy becomes heat. Now you need to capture the heat, transfer it, run a turbine for another power cycle, generate electricity, and send that electricity to the grid. Sounds familiar, right? Because once you get outside the exotic plasma, a fusion plant starts becoming a very complicated thermal power station. And that brings us to the question almost nobody can escape forever. What is the efficiency? What is the uptime? What is the maintenance interval? What does it cost? Because fusion doesn't compete with an imaginary world. It competes with every energy technology available when the plant opens. The business of building a star machine. Imagine you're a utility executive. A fusion company walks into your office. They show you astonishing plasma results, record temperatures, great confinement, powerful magnets, brilliant scientists. You say, wonderful. How much for the plant? How long will the construction take? What's the capacity factor? How often do I need to replace the diverter? Where does tritium come from? What's the overnight capital cost? What's the financing risk? How much power does the facility consume internally? How many employees maintain it? What happens during unplanned shutdowns? What price do I sell electricity for? Those questions are far less glamorous than fusion temperatures. They are also the questions that determine commercialization. This is where private investment changes the psychology of the field. Scientific research can pursue knowledge even if it never becomes cheap. A company eventually has to sell something. DOE says more than $10 billion in private capital is already moving through the American fusion sector. That is significant. But money is not scientific evidence. Investment tells you people believe an opportunity exists. It does not prove the opportunity will work. History is filled with expensive technologies that failed. It also filled. Strike that. History is filled with expensive technologies that failed. It's also filled with expensive technologies that look ridiculous until engineering caught up. So we need to resist two biases: technological utopianism, fusion will never solve everything, and technological cynicism, fusion has been delayed before, therefore fusion can never work. Neither position does the engineering. The engineering lives in the middle. Materials improve, magnets improve, simulation improves, manufacturing improves, but then each improvement has to integrate. That's the key word, integrate. A commercial fusion plant does not get to select only the best subsystem. It doesn't matter if your magnets are extraordinary, if the fuel cycle fails. It doesn't matter if your plasma is stable, if the diverter dies every month. It doesn't matter if the reactor produces heat. If maintenance destroys the economics, every major subsystem to work together. And then the combined machine has to beat the competitors. That's where the energy landscape becomes important. Suppose a fusion plant arrives in 2030. It isn't competing against the power grid of 2026. It's competing against whatever solar costs in 2038, whatever battery storage costs, whatever advanced fission look like, whatever geothermal looks like, whatever transmission infrastructure exists, whatever natural gas costs, whatever carbon regulations exist, whatever grid demand looks like. Fusion's business case is moving against a moving target. And that's why commercial fusion can't be judged solely by, can it generate power? Almost anything can generate power if you spend enough money. The better question is, can it generate power society wants to buy? Reliable, scalable, maintainable, financeable, regulatable, competitive. That is the moment of truth. The test that actually matters. Let's return to our opening machine. Plasma growing, fusion reactions happening, headline announcing another milestone. Now we know how to ask better questions. Question 1. Does the entire facility produce more usable electricity than it consumes? Not just the plasma, the facility. Question 2. Can it operate repeatedly and reliably? Reliably. Not for a record pulse, for the kind of schedule an electrical grid expects. Question 3. Can the components survive? Neutrons, heat, radiation, mechanical stress, fears of operation. Question 4. Can the fuel cycle sustain itself? Can the plant obtain, breed, recover, process, and recycle tritium reliably? Question 5. Can it be maintained? How often does it shut down? How long does it take to repair? Question 6. Can we convert the fusion energy into electricity efficiently? Question 7. What does the electricity actually cost? And maybe that's the only scorecard that ultimately matters. Because the history of fusion has been filled with milestones. Important milestones. Real milestones. But commercialization is different. Commercialization is when the technology stops asking science for permission and starts asking economics for permission. That doesn't diminish the science. It completes the test. Now, consider the DOE target. Mid-2030s. That's aggressive. Maybe the timeline holds. Maybe it slips. The roadmap itself acknowledges dependence on future funding and partnerships. We should not turn the government goal into a prediction. But something has changed. There is now more pressure to define what success means. And that's healthy. Because ambiguous finish lines allow technologies to remain promising forever. Fusion needs a scoreboard, not hype. Not cynicism, a scoreboard. Net electricity, availability, component life, tritium balance, maintenance time, capital cost, operating cost, electricity price. If those numbers work, commercial fusion has arrived. If they don't, then the research continues. And maybe that's exactly where fusion should be after 70 years. Not at the end of the story, at the moment where promises begin becoming measurable. So here's the question I want to leave you with. What would convince you? A 5-minute plasma? A 1-hour plasma? A reactor producing heat? A pilot plant exporting electricity? A plant operating continuously for a year? A utility signaling a long-term power contract? A fusion plant producing electricity cheaper than alternatives? Where is your finish line? Because perhaps the most important thing fusion can do next isn't break another physics record. It tells us exactly what victory looks like. Before the next headline arrives, if today's episode made you think, don't stop here. Read the research, study the history, examine the original documents, listen to the experts, listen to the critics, listen to the people who disagreed with you, listen to sensational claims, question the official explanations, question the headlines, question the experts, Question your assumptions and question mine. Because Rabbit Holes Deep Dives is not about handing you a conclusion. It's about following the evidence, even when the evidence leads somewhere uncomfortable. When evidence changed your thinking, which claim deserves more investigation? What did we miss? Which assumption should we challenge next? And what rabbit hole should we go down next? Share this episode with someone willing to examine the evidence, join the conversations, challenge the ideas respectfully, keep asking questions, because every answer opens another question. And every question leads us farther down the rabbit hole. My name is Leroy Nellis, and this is Resilience Radio. Godspeed, stand for the Constitution, and never surrender your ability to think for yourself. God bless, and good night. Hey, everybody. I wanted to sit down with you today and talk about something we've been working on behind the scenes for quite a while now. First, I want to thank you. Whether you've been here from the beginning or you just found the channel recently, I want you to know that I genuinely appreciate every single one of you. Every comment, every conversation, every suggestion, every word of encouragement has helped shape what Resilience Radio is becoming. This isn't just my channel anymore. It's about a community. And because of that, I wanted you to hear these changes directly from me. Over the last several months, we've been doing something a little unusual. We've been studying our analytics almost obsessively. Not just YouTube analytics, but the analytics coming from Naomi, the AI production system we've been building from the ground up. We've been asking questions like, what videos do people come here for? What keeps people watching? What topics naturally fit together? And what happens when we mix very little types of content on the same channel? After looking at thousands of data points, we came to one conclusion. It's time to let each series become a very best version of itself. So today, I'm excited to announce that Rabbit Holes is becoming its own dedicated YouTube channel. Rabbit Holes deserves its own home. It's where we dive into mysteries, history, unsolved questions, and rabbit holes. Strange events, forgotten stories, and all of those fascinating topics that make us lose track of time. By giving Rabbit Holes its own channel, YouTube can better understand who those videos are for. Our AI can learn from much cleaner data, and we can build something truly special for people who love those deep dives. Resilience Radio will continue doing what has always meant to do, help people understand themselves through psychology,
You pushed me down, thought I'd stay on the ground, counting me out like the numbers didn't matter. But pressure builds diamonds in the dark, and I've been sharpening my edge in the chatter. Every scar turned into strategy, every setback fueled my clarity. I took the hits, learned the game, turned my losses into flame. Now I'm coming back strong, and you'll remember my name. I'm rising through the fire.